Hello students, myself Untitled Gorane from RBNB College Srirampur. In last two lectures we have studied about dual nature of radiation and matter from 12th science. We know photoelectric effect, the emission of electrons from a metal surface when radiation of suitable frequency is incident on it. It's called as a photoelectric effect, and the current which flows through the circuit is a photoelectric current. The electrons emitted in this process are the photoelectrons, and we also know the experimental setup of that photoelectric effect, and we have studied the different concepts related with that photoelectric effect. That is the threshold frequency, the minimum frequency of incident radiation for which photoelectrons are emitted from the metal surface is the threshold frequency. Below the threshold frequency, photoelectric emission is not possible. It is possible only when incident frequency is greater than that minimum frequency. We call it as a cutoff frequency, and we also know different observations from that photoelectric experiment. Now today we see the failure of wave theory to explain observations from experiments on photoelectric effect. Failure of wave theory. Failure of wave theory to explain observations from experiments on photoelectric effect. Experiment on photoelectric effect. Wave theory fails to explain some observations from the experiments on photoelectric effect. Now, this wave theory of electromagnetic radiation could not explain many observations of photoelectric effect. The first is, it was observed that there is no time lag between incidence of radiation and emission of photoelectrons. It means, according to that experimental observation, there is no time lag between the incidence of radiation and emission of photoelectron. It means the photoelectric emission is an instantaneous process. As soon as light is incident, photoelectrons are emitted, or as soon as light is stopped, photoelectric emission also stops. But according to wave theory, all electrons near the surface will absorb the energy. All electrons, when light is incident on the surface, all electrons near the surface will absorb the energy, and the metal surface will require a reasonable time. Metal surface will require reasonable time to accumulate sufficient energy to knock off the electrons. When the light is incident, according to wave theory, when the light is incident on the metal surface will require the reasonable time. For what purpose? To accumulate the sufficient energy to knock off the electrons or to emit the electrons. It means, according to wave theory, this concept is not explained. That is, there is no time lag between the incidence of radiation and emission of photoelectrons. According to wave theory, it needs some time. So this is the failure of the wave theory to explain this observation. Second failure is, according to concept, light having large intensity must have a large energy. Then electrons are expected to be emitted with large kinetic energy. One main concept is, if incident light has large intensity, it must have large energy, and if intensity is more, energy will be more, the electrons are expected to be emitted with large kinetic energy. But from this experiment, the observation shows that maximum kinetic energy does not depend on intensity, but it depends on the incident frequency. From this experiment of the photoelectric effect, the observation is maximum kinetic energy does not depend on the intensity, but it depends on the frequency. This is the second failure of the wave theory to explain the observation of photoelectric effect. Then third is, wave theory expected that photoelectrons to be emitted for any frequency if intensity of radiation is large enough. According to wave theory, it is expected that photoelectrons are emitted for any frequency if the intensity of light was large enough. But according to observations of this experiment from the photoelectric effect, the observation indicates that below threshold frequency, photoelectrons are not emitted, whatever may be the intensity of radiation. Photoelectrons are not emitted, whatever may be the intensity of incident radiation. This is the next failure of wave theory to explain the observations of photoelectric effect. Now here, from these experiments, these are the failures of the wave theory to explain these assumptions. Now we know metals have large number of free electrons, hence metals are good conductors of heat and electricity. As they have a large number of electrons, free electrons, they are good conductors of heat and electricity. These electrons are free to move inside the metal. We say that the electrons are confined in a metal. They cannot escape from the surface of metal unless sufficient energy is supplied to it. Electrons are free inside the metal. They are confined in the metal. They are randomly moving in the metal. But they cannot escape from the metal surface unless sufficient energy is supplied to the electron. And that energy is called as photoelectric work function. Photoelectric work function denoted by phi 0, or it is simply called as work function. That is the work function or photoelectric work function. The minimum amount of energy required to be provided to the electrons to pull it out from the metal surface is the work function of the metal, or it is the minimum energy required for the electron to escape from the metal surface. When light is incident on the metal, this minimum amount of energy is called as work function of the metal, or it is a photoelectric work function denoted by phi 0. This photoelectric work function depends on properties of metal. It depends on properties of metal and nature of its surface. It depends on property of metal and nature of its surface, and it is different for the different metals. Different for different metals. as it is a property of metal, and it also depends on the nature of its surface. So this work function is different for the different metals. For example, for potassium, it is 2.3 electron volt. This photoelectric work function is 2.3 electron volt. For sodium, it is 2.4 electron volt. Different values. For zinc, it is 3.6 electron volt. So it is different for the different metals, as it depends on the property of metal and it depends on nature of its surface. It is different for the different metals. Now we see Einstein's postulate of quantization of energy and a photoelectric equation. Einstein's postulate postulates of quantization of energy. And we also see the photoelectric equation. Very important equation, Einstein's photoelectric equation. Now Planck's theory of black body radiation was extended by the Einstein. Black body radiation theory was proposed by the scientist Planck. That theory is extended by the scientist Einstein, and he explained the different phenomenon related with the photoelectric effect. Einstein proposed that under certain conditions, light behaves as if it is a particle. Light behaves as if it is a particle. We know wave nature of light. But according to Einstein, under certain conditions, light behaves as if it is like particle, or it was like a particle, and its energy is released or absorbed as a bundles. Energy of light is released or it is absorbed in the form of bundles or quanta. Sometimes light behaves like a particle under certain conditions, and its energy is released or absorbed as a bundles, or that bundles is also called as quanta. The quantum of energy of light is called as photon. Quantum of energy of light is called as photon. Quantum of energy of light is called as photon, and the photon, each photon is having energy E is equal to h nu. This is energy of photon. Nu is the frequency of light. H is Planck's constant. This constant is called as Planck's constant, and its value is 6.626 into 10 raised to minus 34 joule second. Light energy is released or absorbed in the bundles or quanta. Quantum of energy of light is called as photon. Energy of each photon is given by the h nu. H is Planck's constant. Nu is the frequency of light, and value of that Planck's constant is 6.626 into 10 raised to minus 34 joule second. Now this E equal to h nu is relation between particle like nature, that is energy, and wave-like nature, that is the frequency. This relation relates the particle nature and wave nature. Particle-like nature, that property is the energy, and wave-like nature, that property is the frequency. So this relation is Einstein's relation, and the photon moves through space with speed of light. We know speed of light is very high. Photon moves through space with very high speed, that is 3 into 10 raised to 8 meter per second. So this is Einstein's postulate about the quantization of energy. And now we see Einstein's photoelectric equation. This equation is very important in this chapter. Einstein's photoelectric equation. When radiation of frequency nu is incident on a photosensitive surface, we know that in photoelectric emission, this is the emitter plate, radiation is incident on this surface, and photoelectrons are emitted like this. These are the photoelectrons. There is evacuated tube, we know all this. This is emitter, here there is a collector, this is connected to battery, here there is a quartz window. When this radiation is incident on a metal surface, or that is the emitter, the photoelectrons are emitted. When the radiation of frequency nu is incident on a photosensitive surface, that is this surface, there are collisions between photons and electrons in the atoms of emitter, because radiation is in the form of photon. When this photon is incident here, there are collisions between photon and electrons in the atoms of the emitter. What happens during these collisions? During this collision, entire energy of photon is transferred to the electron without any time lag. Without any time lag. It means energy of photon, we know it is h nu. This is energy of photon. When this photon is incident, this energy is incident, there is a collision between the photons and the electrons, and during the collision, entire energy of photon is transferred to the electron without any time lag. This energy absorbed by the electron is used in two ways. This h nu is used in two ways. First way is, part of this energy is used by the electron in liberating itself from the atom. Part is used to liberate the electrons. From the metal. And we know this part we call it as photoelectric work function, or it is work function. Part of the energy is used by the electron to liberate itself from the atom, and that part is photoelectric work function. The remaining part of this h nu appears as kinetic energy of electrons. Remaining part appears as a kinetic energy of the electrons. During this process, if electron does not lose any part of this energy, or it does not lose any part of the energy in collision inside the surface, then it escapes with maximum kinetic energy. This kinetic energy will be maximum if there is no loss of energy during the collision. This energy is used in two ways. Some part is used to liberate the electrons from the metal. We call it as a work function, phi 0. and the remaining part of energy appears as the kinetic energy of the electrons. But if during the collisions, if there is no loss of energy, the electrons escapes with the maximum kinetic energy, and we call it as 1/2 mv square max. This kinetic energy, that is the electrons moves with the maximum velocity. Hence, we write the equation as h nu, that is the energy of photon, usually in two ways, that is some part is used to liberate the electrons, that is the work function. Remaining part appears as the kinetic energy, and if there is no loss of energy, electrons moves with maximum kinetic energy, and we call it as 1/2 mv square max, or we write it as kinetic energy maximum. Hence, Ke max, kinetic energy maximum, is equal to h nu minus phi 0. This equation is Einstein's photoelectric equation. Einstein's photoelectric equation. We can explain different characteristics of photoelectric effect with the help of this Einstein's photoelectric equation, or we write this also as 1/2 mv square max is equal to h nu minus phi 0. Kinetic energy maximum is equal to 1/2 mv square max. But in previous article, we also know this 1/2 mv square max is equal to E into V0. E is the charge on the electron, magnitude of charge on the electron, and V0 we know it is the stopping potential, that is the minimum retarding potential given to the collector for which photoelectric current becomes 0, and in that article we know that 1/2 mv square max is equal to E into V0. Hence, we also write this equation as, instead of 1/2 mv square max, we write it as E into V0, that is h nu minus phi 0. So this is about the Einstein's photoelectric equation. Okay students, today we stop here. Thank you.